Glass is known for its transparency, but also for how easily it can shatter in an instant. It's hard to believe that from this very waste material, humans have created foam glass, a substance harder than stone, resistant to fire and water, and nearly eternal. What once seemed like useless shards now begin a new journey. After being collected and melted, the glass crystallizes into millions of closed air cells, a structure that gives foam glass its form and makes it capable of lasting for centuries without changing shape or properties. In this video, we'll explore how discarded glass is reborn into a material that's almost indestructible, where waste becomes stone and recycling transforms into a symbol of lasting power. Every year, the world produces over 130 million tons of glass, tens of millions of which are recovered and recycled, fueling a $2 billion industry, foam glass. Born from regenerated glass, foam glass is more than just a construction material. It is the fusion of science and sustainability. Its structure of millions of sealed air cells makes it both lightweight and strong, completely fireproof and impermeable to water. Each foam glass block is carefully packaged in sheets or panels, ready to serve as the foundation, roof, or insulation layer for structures built to last. It is a paradoxical journey where one of the most fragile materials ever known transforms into a symbol of strength and renewal. To produce foam glass, the glass collection stage serves as the starting point of the recycling cycle. Factories prioritize sourcing industrial glass waste, such as construction glass, flat panels, and bottles, because these materials are far purer and more consistent than household glass. Collection takes place through a tightly connected network linking demolition sites, glass manufacturers, and material recovery centers, forming a closed-loop supply chain. In Europe, where the foam glass industry is particularly strong, this system is capable of recovering hundreds of thousands of tons of glass each year, meeting the majority of the raw material demand for production plants. Maintaining a stable supply of recovered glass not only reduces the strain on natural resources, but also ensures the sustainability of the entire foam glass manufacturing process, where every shattered fragment is treated as a vital link in the material's journey of renewal. After collection, the waste glass is transported to specialized sorting facilities. This is the first stage of the treatment chain, where all incoming materials are reevaluated to ensure that only glass meeting strict standards will be used in foam glass production. Here, the glass is separated by color and purity, primarily into clear, amber, and green categories. Sorting by color not only maintains optical consistency, but also directly affects the chemical reactions during the melting process. Automated systems equipped with optical sensors continuously scan the glass surface, detecting and ejecting unwanted materials such as metals, ceramics, stoneware, or plastics with air jets timed to the millisecond. The approved glass fragments then undergo a final manual inspection, where workers remove any remaining contaminants that machines may miss, particularly multi-layer or coated reflective glass. Thanks to this meticulous process, the purity level of the raw material can reach over 99.7%, meeting the demanding requirements for foam glass to form its perfect closed cell structure. Only after passing the sorting stage are these once fragile glass pieces truly ready to enter the grinding phase, where they are transformed from discarded waste into a technical feedstock for a material designed to last for centuries. Once the glass has been properly sorted, it is transported to the raw material grinding area, where uniform fragments are reduced to cullet, fine glass granules of consistent size and texture, ideal for the melting and foaming process of foam glass. Depending on the glass type, the material is fed into either hammer mills or ball mills. The hammer mill serves as the primary crusher, rapidly breaking down thick glass sheets through the impact of high-speed rotating blades. For batches requiring finer granularity, the glass undergoes further refinement in a ball mill, where thousands of steel balls rotate continuously, grinding and polishing the particles through friction. This dual-stage process produces cullet that is not only uniform in size, but also consistent in density, forming the foundation for the stable, high-quality structure of foam glass to come. Once the grinding stage is complete, the glass material moves through an automated screening and inspection system, a critical step to ensure every cullet particle meets the required size and purity before mixing. On a vibrating conveyor, multi-layer sieves operate continuously to separate the particles by size. The optimal cullet size for foam glass ranges between 0.1 and 2.5 inches, a carefully calculated range that ensures fast, stable melting and uniform foaming inside the furnace. After screening, the material passes through optical and magnetic sensors, where industrial cameras and metal detectors analyze each moving stream of cullet. These sensors can detect even microscopic contaminants, such as ceramics, stoneware, or metal fragments just a few thousandths of an inch wide, and remove them instantly with pinpoint air jets. In modern foam glass facilities, this system achieves up to 99.9% accuracy, virtually eliminating any impurities that could affect the closed cell structure of the final product. Finally, the qualified cullet is transferred via enclosed conveyors to storage silos, where each batch is labeled and organized according to particle size. From here, the material is ready for the mixing stage, carrying the exact precision that every step of the process has worked meticulously to achieve. Once the glass has been ground into high-quality cullet, it moves to the mixing stage, the final preparation before melting. The goal of this phase is to create a uniform blend of glass powder and foaming agents, which will generate the signature closed cell structure of foam glass. The cullet is fed into an industrial spiral mixer along with a small amount of foaming additives, such as carbon powder, fine coke, or sulfur-rich inorganic compounds. The mixing ratio is extremely low, typically around 0.4–0.6% of the total glass weight, yet it determines the final material's density, porosity, and thermal insulation performance. During the melting phase, these foaming agents decompose and release CO2, forming millions of sealed air cells within the molten glass mass. To ensure consistency, the blend is slowly stirred by low-speed helical paddles that maintain even distribution and moisture control. Once mixing is complete, the glass powder blend is fed into a wet rolling system, a crucial shaping stage before drying and firing. Instead of being dry rolled, the material is spread into a thin layer and passed through rotating rollers, partially submerged in water. This water film allows the mixture to spread evenly, reduces friction, and stabilizes the surface, while also providing the necessary compression to achieve a uniform density throughout the layer. As the material exits the rollers, it forms a stable, thin sheet that retains just enough moisture to hold the glass particles together. After drying, the blended layer is fed into a continuous furnace, a sealed system capable of maintaining extremely high temperatures and precisely controlling each stage of the material's transformation. Inside, the process occurs at roughly 1650 to 1800 degrees Fahrenheit, about 900 to 1000 degrees Celsius, hot enough to melt the glass but not so high that it destroys the foam structure. As the temperature rises, the glass powder softens and fuses into a viscous molten mass. At the same time, the foaming agents such as carbon or calcium carbonate begin to decompose, releasing carbon dioxide gas. These gas bubbles become trapped within the softened glass, forming millions of closed air cells, the distinctive structure that gives foam glass its thermal insulation and waterproofing properties. The heating rate is controlled with extreme precision. If it increases too quickly, the gas escapes before the glass becomes pliable enough to retain the bubbles. If too slowly, the foam structure collapses, increasing density and reducing insulation performance. For this reason, foam glass production lines use zone furnaces where each section operates at a specific temperature and residence time, typically totaling 45 to 60 minutes for the entire cycle. By the time it exits the furnace, the foam glass block is fully formed, lightweight yet solid, with a density of about 8 to 15 pounds per cubic foot, far lighter than concrete but with remarkable compressive strength and dimensional stability. It is at this stage that glass, once fragile, is reborn as an almost eternal form of artificial stone foam. When it exits the furnace, foam glass is not produced as individual pieces, but as one continuous block, a large slab stretching several tens of feet in length. At this stage, the material has cooled slightly and its cellular structure has stabilized, yet it remains brittle like glass. To achieve the final product dimensions, the factory proceeds to a stage known as breakout, the controlled fracturing of the foam glass block. The entire slab is placed onto a vibrating conveyor equipped with offset rollers that generate a precisely calculated torsional and mechanical vibration, typically between 20 and 40 hertz. Under this motion, the foam glass naturally cracks along internal stress lines formed during melting and cooling. These lines are intentionally engineered by controlling thickness, airflow direction, and furnace temperature, allowing the block to separate cleanly along predefined grids without the need for cutting tools. No blades, saws, or cutters are used. This contactless method preserves the integrity of the closed cell structure and prevents bubble collapse or edge burning from heat friction. Each fracture leaves a slightly rough, natural surface that improves mechanical adhesion when the foam glass panels are later bonded or plastered during insulation installation. The fractured blocks are then collected and fed through an automated sizing system, which sorts pieces by thickness, typically 2 to 6 inches, and density, about 8 to 15 pounds per cubic foot. Smaller fragments or irregular edges are not discarded. Instead, they are recycled back into the grinding and mixing lines, allowing nearly 100% material reuse. In the foam glass industry, breaking is far more than just splitting a slab. It is the moment when a once fragile substance becomes a finished product. After being fractured into standard-sized blocks, foam glass is not stacked manually onto pallets, but instead transferred directly onto the automated packaging line. Conveyor belts carry the blocks to a dosing hopper, where they are dispensed straight into specialized polyethylene bags designed to resist moisture and ultraviolet radiation. Each bag is filled to a fixed weight, typically between 15 and 30 pounds, then heat-sealed to remove excess air, ensuring stability during transport. This protective film not only shields foam glass from dust and humidity, but also helps preserve the internal cell structure and density throughout storage. Finally, each package is labeled with batch information, production codes, and technical specifications before being palletized or loaded directly into shipping containers. From there, these stone foam blocks, born from recycled glass, continue their journey, carrying the strength of sustainable materials to building projects across the world. Once the foam glass blocks are fully packaged, their journey inside the factory comes to an end. But this marks only the beginning of their true purpose in the world of construction. In industrial applications, foam glass is used as an insulation layer for flat roofs, basement floors, exterior walls, storage tanks and chemical pipelines, environments that demand complete impermeability and corrosion resistance. In the energy sector, the material encases pipelines carrying oil, gas, and liquid nitrogen, maintaining thermal stability and preventing condensation, something most other materials cannot achieve. Thanks to its total chemical inertness and ability to withstand temperatures from 450 degrees Fahrenheit up to over 900 degrees Fahrenheit, foam glass remains durable against solvents, acids, and even microorganisms. With compressive strength exceeding 100 pounds per square inch, it can be installed beneath factory floors, concrete roofs, or heavy machinery foundations without deformation. From cold storage facilities and power plants to towering skyscrapers, foam glass is more than just an insulating material. It is a sustainable shield born from recycled glass, proof of how humanity can transform one of the planet's most fragile substances into a foundation of enduring strength for the future. Behind every block of foam glass lies proof of how humanity can turn waste into technology, transforming one of the planet's most fragile materials into man-made stone that can endure for centuries. It is not merely a product of recycling, but a symbol of precision engineering and sustainable thinking. where material science meets the spirit of global resource conservation. Its closed cell structure, resistance to fire, water, and compression make foam glass one of the most remarkable materials ever created in construction. Yet its true value goes beyond performance. It lies in the message it carries, that there are no limits to renewal when we are wise enough to see potential in what has been discarded. In a world where industry and the environment must increasingly coexist, foam glass reminds us that sustainability doesn't begin with the future. It begins with how we reinvent the present.